Hi, everybody, and welcome to. I guess this isn't a model video. Anyway, a bunch of people had questions on the discussion forum, and some people emailed me about dot notation. So here I'm going to try to explain in a little bit more detail how this works at a technical level. Um, I didn't do this the last time I taught the class, and part of that's just because I understand this stuff intuitively. I saw a bunch of examples when I learned it, and that was good enough, and it seemed to be good enough for most people. But in case you are confused still, I will try to go over a few examples and explain how the dots work. So there are two things that a dot in our system can do. The first thing is a dot can mark conjunction or represent conjunction. So, if we have two alternations, we want to conjoin them. Right, so here, this dot, all it does is it marks conjunction. Right. The other thing that a dot can do is to attach to one of our other operators, or the arrow, the biconditional, to mark grouping on one side. And the reason why I didn't go into incredible detail about how this works is I'm actually doing something different than Quine's book, the official book does. So for Quine, but not for us, the conjunction marking function of the dots has less precedence or priority. And the dots that attach to one side of the groups have more priority. But we're just ignoring that. So instead of taking that as a rule, I'm just having you use the dots to mark priority. How do I say this? Like evenly. So I'll explain that. Probably confused a bunch of you, but I'll try to explain what I mean with an example. So let's consider just making this up. The schema, I don't know, P, if P, then if Q, then R. Actually, wait, let's do this. Okay. I'm not going to read that, but it's a bunch of conditionals inside of a big conditional. Okay. So how we would convert this, I'll just put it into dot notation real quick, is like this. Okay. So here we only have operators that do the second thing, that attach to one of the operators to mark grouping on one side. So how this works is, at a technical level, is see these, let me zoom in, see these two dots right here, right? So they're on the right side of this conditional, and what that means is that they mark a group that extends in the direction of the side of the operator they're on, right? So these dots mark a group in this direction. Oops. Right, and that group continues until you reach a number of dots that are equal or greater, or until the schema ends, right? And so this dot here, right, does the same thing. It's on the right side, so it marks a group to the right that continues until you reach a dot of equal or greater number, or until the schema ends, right? And bigger groups swallow smaller groups, I guess. That's not very technical, but I'll explain what I mean. So let's move this real quick so I can do some stuff to it. So another kind of another visual way in which you might get a hold of this is you can do this. So instead of drawing lines under the groups, I'm going to draw vertical lines. So start with our biggest group of dots, which is these 2 dots. I'm going to draw a line that it's like big, right? And then our second group, the single dot, I'm going to draw a smaller line. And because both of these are on the right side of the operators, the group that they mark extends to the right, and it extends until you reach either the end of the schema or an equal or greater number of dots. So this is kind of another visual way of representing what the dots do. So I think part of what confuses people is that I sometimes use dots on both sides of the operators, and that's actually fine. So just write this stuff. So you could, I'll show you with the boxes in a second. You could do something like this if you really wanted to, and it would end up the same, sort of. So I'll show you what I mean. I'll do 2 different colors here. So again, we'll do the right side dots first. So we have big box, little box. Right. Now, if we look at the dots on the other side, I hope this is helpful. So we have, big, little, right? So same thing goes in the other direction, right? So for the big box over here, it's just this P, right? Because we have 2 dots, we keep going left until we reach an equal or greater number of dots or the end of the schema. For the Q right here, we keep going until we reach an equal or greater number of dots, and we have 2 dots right here, right? So it's not always the case that if you just put the same number of dots on both sides of the operator, it'll end up the same. Or I don't know that it is. It might be, actually. I don't know how to prove that off the top of my head, right? But so the reason why I will do stuff like, this is really just for clarity. And if you apply the kind of the rule or method that I'm explaining about, just like follow the dots on the side of the operator they're on till you run into an equal or greater number of dots, it'll be perfectly unambiguous even if I use more dots than are strictly speaking necessary, right? So, we have this goes to the left until we run out of schema. This goes to the right until we run out of schema, right? It's a conditional. It's pretty straightforward. Give me a second to pull up the logic book, and I will do one of the harder homework ones. 1 second. Yeah, sorry. This is improvised, just to help people. I don't have my phone. Oh, fuck it. I'll just make one up. Okay. So let's get a really obnoxious schema. So like P or not Q, therefore R, if and only if S or T. And let's do is that well formed? Yeah. Okay. Actually, let's make this a conditional. And then let's do it like this. Okay. Is that well formed? P O yeah, it's well formed. Okay. So to put this into dot notation, one trick is that most of the time, so see how we have 3 different kinds of brackets or parentheses here? That tells us that we're probably going to need at least one single dot, at least one double dot, and at least one triple dot. So this would go, again, I'm just going to do it. Yeah. 2 Q R if only if S then for T. Okay, and this is kind of the minimalist way of doing this without stuff on both sides. So again, let's do our box thingy. I'm going to start with the biggest one first. So we have this triple dot, right? It's on the left, this triple dot. It's on the left side of this arrow. So we draw a big old line like here, and then we follow it out to the left until we reach an equal or a greater number of dots where the schema ends. So we get to the end of the schema, right? So that's one group. Then we have our double dot on the right side of this, the V that represents alternation. So we draw a little bit of a bigger thing there, or a smaller line there. We follow it until we reach dots of equal or greater size. 3 is bigger than 2, so we stop there. Right, then we have this single dot here, so we draw a smaller vertical line. We keep going to the right until we reach dots of equal or greater size. We get to the 3, right? And remember, bigger groups, the way I'm doing this, swallow smaller groups. Very technical, logical term there. So that. Then we close this here. And then on the right side, we just have this T here, right? So let me make up another one just to show you. And again, if there's sometimes we'll have stuff like, here, I'll show you one of the ones that like we'll see later, like P or Q, not Q, therefore R, if and only if S or T or W. Okay, so let's make this biconditional the main operator. So I'm going to do this in parentheses first, just to do it in parentheses first. So you can see S or T, Q, R. Is that well formed? Yeah, I think it is. Okay, so to put this into dots, so here, again, we have, hopefully my heuristic works here. We have 2 different kinds of parentheses in our original formula. We have square brackets and good old-fashioned parentheses. So we know that we're going to need at least one group of 1 dots and at least one group of 2 dots. So how we would do this is we do P or not either for R, if and only if S or T or W. Oh, actually, wait, no, this can be just S or T or W. I forgot about the commutativity of alternation there for a second. Actually, if we change this to an arrow, we'll need the dot. So let's change that to an arrow. And then like this. Okay, so let's follow our procedure again. So, and here I believe we actually do need dots on both sides of the biconditional. But even if we don't, and I'm pretty sure we do, it's prettier with the 2 dots. It makes it clear that the whole thing's a biconditional. So that's one of the reasons I will do that. So let's start on the left here with this. So we draw our big line. It extends until we reach 2 or more dots or the end of the schema. We don't have 2 or more dots anywhere, right? So end of the schema. On this side, same thing. Group extends to the end of the schema, right? Then our smaller dots, so they are, oh wait, no, that's fine. So starting on the right side, we have this, and so we draw a smaller line. It's on the left side of this arrow. So we follow it until we reach equal or greater number of dots, or the end of the schema. So we get that. Close it off like that. And on the right side, we just have this W. So the right side's done. Here, we have this dot on the right side of this alternation. Draw our thing, follow it to the till we reach an equal or greater number of dots in the end of schema. So we got that. And then the left side of that's just P. Right. So that's what the dots do. Because of the way they work, there's not like a simple, straightforward, like they'll always be the left parenthesis or the right parenthesis when you transform into dot notation. Yeah. I hope that's helpful. Here, let me go through one more just so you can see how this functions. So let's do one with the negation just so we get the hang of that. This is a little different. Then let's do this. Is that well formed? Yes, that looks well formed. Okay, so here's a case in which you can get away without doing the dots on both sides of the biconditional. So this not if P then Q. It's hard to read stuff like that in English. That we can't do anything else to. That has to stay the same. Remember, when we're negating a whole group, we have to keep the parentheses. So that's in dot notation. And so what I would do here is I would do on both sides of the biconditional have two dots. And again, that's just, I think it looks prettier. We could, if we really wanted to, get rid of that side. But I'm going to leave it because I like it. So then on the right side, it's if R, then S, therefore T. Right. So let's do our thingy again. Actually, let me move this. Okay. So start with the biggest box. So here on the left side, we got our two dots. We could go into the left and we run it in equal or greater number of dots, or the beginning or end of the schema. We get to the beginning. There's nothing else. Similarly, here, right? Then here, right? And so that's why you'll never have a dot at the very beginning or end of a schema, because it wouldn't mean anything, right? So dots aren't just like a one-to-one replacement for parentheses. The point of these, the reason why we bother with them, is that whereas we would need kind of like here we need an opening bracket and a closing bracket, and here we need an opening parentheses and a closing parentheses, we replace each set of brackets or parentheses usually with one dot, but sometimes we'll use two like that. Or sorry, we don't necessarily replace each set of brackets or parentheses with one dot. We replace it with like actually, I forgot to do an example involving conjunction, because conjunction doesn't occur to the side of an operator, so I need to explain how that works. So for conjunction, let's just, I don't know, or black and white. Here's schema. It's ugly. S or T. Okay. Actually, wait, not you. Use a bad letter. It looks like an alternation symbol when I read it. Okay. So here's schema. Yay, woo, schema. So the whole thing's conjunction, right? Conjunction. Right. And here's how we would put it into dot notation. Okay. And so here we have the whole thing's a conjunction. So how does that work? Well, the only difference between a conjunction and the dots on one side of an operator is that conjunction extends the grouping in both directions, right? So we draw on each side of it. We can do it like this, the big line. And again, we keep going until we reach equal greater number of dots or the end of our schema. So we get to the end of our schema. So the whole thing's a conjunction. These big old boxes express the big old groups. So then here we have this dot on the right side of a conditional arrow. Draw our line, keep going, reach the end of the schema. Big boxes eat little ones. Here we have it on the left side of the arrow. So keep going like that. Right. And that's how it works with a conjunction. And again, if you should ignore what I'm about to say if you're not following along in Quine's book. Just turn the video off. It was fun. Like, woo, we did it. But if you look at Quine's book, he will do shit like, or stuff like, oh wait, actually here, let me. Q or R. No, wait, never mind. I need a better example. That's a little weird. So let's do P if and only if P or Q and R. So Quine will do this sometimes, and you're like, what? That violates the rules, and it does. And this is the difference between having an implied higher strength of priority versus I'm just making you express the strength of the grouping explicitly. So remember up above I said that for Quine, the dots that attach to one side of our operators have more priority than the dots that just express conjunction. So if you're looking at Quine's book and you're confused, it's because when he writes this, he means what we mean when we write this, right? So the two dots here as opposed to the one. And it's perfectly like fine. It's just like order of operations in math or whatever. But I find this to be like really painful to read, especially in a really long schema. So we're always going to do the explicit expression of grouping. And that lets us figure this out with our line drawing technique without having to remember which dots have more priority than others. Right? So like that. Yeah. If any of you are following along in Quine's book, I'm sorry for diverging, but I didn't invent this. The guy who taught me this system of logic, Dr. Asher Seidel, he was under the impression that Quine's system with the order priority was kind of painful to read, so he adapted it in this way, and I agree with him. It's a lot more readable. So hopefully that clears up some of the confusion you guys had on dots.